We have finished the first half of the semester on the mainstream memories. And starting from today, we are going to move on to the emerging non-volatile memory. And today we are going to have an overview of the emerging technologies. And later in the following lectures, we will have the emerging technologies to be discussed one by one. And today is just an overview. So this is an outline for today's lecture. So we will first talk about the candidates for the emerging non-volatile memory, and then we will talk about the array architectures for the emerging non-volatile memory, and some design considerations, including the selector and the interconnect. And finally, we will talk about one of the commercialized products for the emerging non-volatile memory. So this is a 3D exponent memory technology invented by Intel and Micron. So this is a quick recap. We mentioned this memory hierarchy at the very beginning of the semester, and we have already discussed the SRAMs for the cache, and you have L1, L2, L3 caches depending on the speed you may need. And then there's a trade-off within the cache hierarchy. And you know you have to size the SRAMs W over L in order to meet the demand for different levels of the cache. And typically SRAM is like a few nanoseconds or even below nanoseconds. And the capacity is kilobyte to megabyte in that range. This is on-chip embedded memory on the same chip with the processor, either your CPU or GPU. They have a lot of caches. And then the DRAM is off-chip. It's a separate chip, unless this is an embedded DRAM, eDRAM. But mostly DRAM is a standalone off-chip memory. And you may have tens of gigabytes of DRAM, and DRAM's row cycle is typically tens of nanoseconds. And this is also volatile memory, SRAM and DRAM. So once you turn off the power, then you lose your data. And then the NAND flash, like your SSD, is non-volatile memory. And this is much slower, like NAND flash read time or the programming time. Erase time is like tens of microseconds to hundreds of microseconds, even to milliseconds. But you can reach hundreds of gigabytes or even terabytes. And this is non-volatile memory for your data storage, right? So, but we do see the gaps between those levels in the hierarchy. That's why emerging non-volatile memory may play a role in those gaps between those levels. So we do see those gaps in terms of the latency, speed, or the capacity. So that's the motivation for the emerging non-volatile memory technologies. We need the larger memory capacity and the ever-increasing bandwidth to meet the demands. And then the energy consumption and leakage power is also a concern for the system design. And many of those mainstream technologies we discussed so far, like SRAM, DRAM, flash, facing challenges in the future scaling. Then what would be the attributes for an ideal memory? So if you want an ideal memory, so the following attributes are what you want. So you may not have all of those attributes together, simultaneously in one memory candidate, but this is your wish list. So you want the memory to be non-volatile. That means you can keep the data after the power is off. And you want high density, small area per bit, no power consumption, and bit writable. This is like the random access memory. You want to direct write without prior erase. This is respect to the NAND flash we discussed before. So you have to do the block erase. And you want fast read and write, non-endurance, That means many cycles for the read or the write. And then no cost for the fabrication, no voltage supply, compatible with your logic voltage supply like below 1 volt, and scalable, compatible with the CMOS technology. So there's no universal memory that can satisfy all the requirements at the same time. That's why we have this memory hierarchy, right? Different memories serve different levels in the hierarchy. So if you want to make a memory, what you need is really a hysteresis in the device property. So you want at least 2 levels that is in the hysteresis loop. So if you look at the mechanisms, basic mechanisms to make a memory, so you can categorize that into first the charge storage mechanism. So for example, you can store the charge in a capacitor. For example, the DRAM, right? You make an explicit like a cylinder-like 3D cylinder-like capacitor to store the charges in the DRAM. Or in the SRAM, essentially you rely on the parasitic cap in those 2 storage nodes to store the charges. And the flash, actually you also rely on the charge on the trap side, like in the floating gate, you store the charges there, or in the like charge trap transistor, you store the charges in those traps. So essentially you rely on the charges to store your memory state. If you have a charge, then you have, for example, memory state 1. If you don't have charge, then you have memory state 0. So you rely on the charge. So those are charge-based memory we discussed so far. But in the next, we are going to discuss emerging memories. Most of them depend on other mechanisms. For example, you can rely on the resistance change. So you can use high resistance state to store like information 0 and low resistance state to store the information 1. There are different mechanisms to do that. You can rely on the phase change of the material, or rely on the conductive filament formation, or rely on the spintronic effect to change the resistance. So those processes involve changing the atom in the material, and we are going to discuss in the next. And finally, there's a ferroelectric material. This relies on changing the capacitance of the state. So here we are going to discuss the following mechanisms in today's lecture and the following 3 or 4 lectures. So here, charge-based memory face the scaling challenges as we discussed. So here we show the DRAM, SRAM, and floating gate transistor, flash. So as we just discussed, all of them rely on the charge storage, either at the internal capacitor or this internal parasitic cap by those like CDB, CGD of those transistors, and also rely on the charge storage in the floating gate or the charge trapping layer. So the challenge is that in general, as you scale this technology node, then the area or the volume to store those charges reduce. Therefore, you don't have many charges in the storage node, and then that will cause the like a sense margin degradation or the reliability problems as we discussed if you only store few number of electrons in those storage nodes. Okay, so then let's move on to the emerging non-volatile memory, and we are going to have them have an overview for each of those technologies, and we will dive into the deep physics later in the following lectures, but today is just a principle. So the first one is this spin transfer torque magnetic random access memory, or is short for STT MRAM. STT for spin transfer torque, MRAM is magnetic random access memory. And this device relies on the structure based on this kind of MTJ structure, magnetic terminal junction. So here is a sandwiched structure. You have two ferromagnetic layers, mostly made of this cobalt iron boron. So they are separated by this oxide terminal barrier, mostly made of the MgO. And then here you can think those are two little magnets. And the magnet, you know, they have the magnetization direction, like the south pole, north pole. So here the bottom layer is a pinned layer, and in this case, the magnetization always point to the right. So this is a fixed layer. And then the top layer is a free layer. That means the magnetization direction can be changed, either left or right, depending on the current flow through this vertical stack. So but here we have a property that is depending on the configuration of the two magnetic layer or two magnets. If they are in the same direction, here we can call them like parallel states. We have both magnetization pointing to the right. Then this is an on state of the cell. And then if you have anti-parallel at the top layer pointing to the left and the bottom layer pointing to the right. So this is anti-parallel configuration. This is an off state. So here the property is that if you have the parallel state, the resistance across this stack, oops, pen doesn't work. Okay, so if you pass current through this stack, and then you can measure the resistance. If you apply voltage and then you measure the current through the stack, then you can calculate the resistance. So the parallel state resistance is smaller than the anti-parallel state resistance. So you can use the resistance difference to store your memory states. So the parallel state, you can think this is like 1. And the anti-parallel state, you can think this is 0. So when you later sense the state, then you apply a small voltage and then read the current, then you can measure the resistance. So they are different. So this is depending on the resistance change of this MTJ stack. And we will discuss later how we exactly change the configuration. But here, remember that you have a pinned layer that is always pointing to one direction, for example, to the right. And then the top free layer can change its magnetization from the left to the right or from the right to the left, depending on how you write the data. And then the second emerging number memory is this phase change memory. And it's short for like PCM. So here, this is the typical device structure. We have like a top electrode, bottom electrode, and here this region you have like a heater. It's metal. It's like a typically like a tungsten plug. It's metal. And then the phase change material is deposited between this heater and top electrode. So the phase change material typically is made of this chalcogenide material, such as GST. This is germanium antimony telluride. So this GST phase change material has a property to change its phase. So what do we mean by phase? Phase means the configuration or the organization of the atoms in the material. So here if the atoms are arranged in this kind of regular pattern, we call it in the crystalline state. Crystalline is a crystal, basically. So the atoms are arranged regularly in such pattern. Of course, this is a cartoon figure, not necessarily in this kind of like square pattern. It may have complicated crystal structure, but it's repeatable in the 3D dimension, this pattern. And then the phase change material has a property that is once you heat up the temperature by, for example, injecting large current, then you have the Joule heating, and then the temperature of this material goes up. So it's like you melt the material. And then after the melting, so it's like a liquid, right? After melting, it's like a liquid here. Then you do a quick quench process. So you remove the heat rapidly. So the atoms will remain in a random location after you cool down. So then the material changes to this amorphous phase. So amorphous phase means the atoms have random locations. This means this is amorphous phase. And here, if you compare the resistance of this material between those two phases, you will find out the crystalline resistance is smaller than the amorphous resistance. Again, you can use this to store the information like 1 and 0. You sense the difference in resistance. And then if you gently heat up the amorphous state over some period, so the atoms will get some kinetic energy to find its energy minimal state. That is the crystallization process. So the atoms will try to find the regular pattern to be recovered to this crystalline state by a crystallization process. So this is how you change between the amorphous state and the crystalline state. So here you have to play with the thermal profile within the material. And you can do that by shaping the pulse, your voltage pulse, like shape, like amplitude and duration of your pulse to trigger the change between the crystalline state and amorphous state. We will discuss more details later in the phase change memory section. But this is a general mechanism depending on the phase of the material. So any questions so far? All right, then the third candidate is called the resistive random access memory, RRAM for short. And this one also has this sandwiched structure. You have two electrodes made of metal, and between that you may have this oxide layer. And the oxide nominally is insulating, so you have a high resistance state. But if you apply large voltage on the top electrode, then you can create many of those oxygen defects or vacancy. So basically you lock out the oxygen from the lattice, and then the oxygen will become ionized to become oxygen like you apply positive voltage here, then the oxygen will be knocked out from the lattice and become the oxygen ion, and the ion will migrate or will be attracted to the top electrode, and then the oxygen will move to here. So those are oxygen. And then those empty circle is a vacancy. of the oxygen. It's like electron and hole pair. You get out one electron, you get a hole. And in this case, you get out one oxygen atom. What is left behind is a vacancy of the oxygen. So those vacancies form this conductive filament. Electrons can then hop through these vacancies. The current will flow in this conductive filament. Therefore, the resistance is low. You can conduct the current in oxide. And then if you want to switch off, then you apply negative voltage. You can drive the oxygen back. Then this part will be recovered. And then you will recreate some oxide layer in this tunneling gap region. Then the current will be much suppressed, and then the resistance will be high. Again, this stores like information 1. If you have this filament in the oxide, if you don't have the filament or the filament is ruptured, then you have the state 0. So this depends on the resistance change in this stack. To summarize, what we discussed are all resistive non-volatile memory because they depend on the resistance change in the device. And in the STT-MRAM, the one state is the on state, no resistance state, and we sometimes use LRS to represent this no resistance state. And in the STT-MRAM case, you have the parallel configuration of the two magnets. That is the LRS, on state, one state, and the anti-parallel state of those two magnets give you the high resistance state, HRS, or the off state, and 0. And in phase change memory, PCM, so again, the crystalline phase give you the LRS, on state, one state. Amorphous phase give you HRS, off state, 0 state. And R1, formation of the conductive filament in the oxide layer give you LRS, on state, one state. And rupture of the conductive filament give you HRS, off state, 0 state. So the underlying physics are different for those three memory technologies. But from the high level of abstraction, you can think all of them like a two-terminal resistor, right, with variable resistance. Because from the circuit point of view, right, those are two-terminal devices. Essentially, it's a resistor, but you have different resistance, either low resistance state or high resistance state. Right. Of course, the physics is different for those three memories, but from the circuit point of view, then you can think they are a variable resistor with different resistance depending on the state, and then you can store your memory state into the resistance. So any questions so far? And here we show the typical IV current versus voltage characteristics of the resistive memories. And for there are two modes. The first one is called unipolar mode. That means the switching from on to off or off to on can be achieved using the same polarity of the voltage. For example, in this case, so here you apply voltage, you switch voltage from 0 to some positive voltage, and then you can change the device from the high resistance state to the low resistance state. So here you know the slope in the IV is the conductance, right? And then 1 over the conductance gives you the resistance. So in this case, the current is low, that means resistance is high. But after this threshold voltage, then you change the resistance. The current jump, that means the resistance become lower. So this is typically called the set process from the HRS to the LRS. And then in this unipolar mode, you can apply the same polarity. After the LRS, you apply the same voltage, and then it can trigger the LRS back to the HRS switching. So this is called reset. You can apply the same polarity of the voltage, both positive voltage, to change the state in between. And the phase change memory is one of those unipolar mode memory. But to change between those two states, we will discuss later. You have to play with the voltage, pulse, like amplitude, or the pulse width, to trigger the set and reset in the phase change memory. But you can apply the same polarity. You can apply both positive and negative. Because in the phase change memory, what matters is the temperature in the device. So different voltage, pulse amplitude, or pulse width will give you different temperature. But you can apply either positive or negative voltage, doesn't matter, because pure heating, IR square, I square R. I mean, that's just depend on the absolute value of the current you flow. And then the bipolar mode means that you have to be careful about the voltage you apply. Then typically you have to define the reference load. For example, they have 3 layers, typically top electrode, bottom electrode. In between you may have this oxide thermal barrier for the STT MRAM. I mean the 3-layer pin layer and the MGO in the middle. So you have to define a reference electrode. For example, you ground the bottom one and then apply the voltage to the top electrode. So then if you ground the bottom, then use the bottom as a reference. Then you apply positive voltage here. The device first is in the HRS, and then after some threshold voltage is set to the low range state, LRS. And then typically you have to use some compliance current to prevent a hard breakdown of the device. So this compliance current can be controlled either by your equipment or by a series transistor. Later we will say this is typically 1T1R structure. So you need a series transistor to limit the current that is flowing through the cell in the low resistance state. So this current level is limited by the transistor's drive current. And then if you want to switch back to the high resistance state, in this bipolar mode, you have to apply a negative voltage to the top electrode. So that means you reverse this, and then after some threshold, then it will reset from the LRS to the HRS. So here you do need the positive and the negative voltage to trigger the set and reset respectively. And STT-MRAM is bipolar, and most of the R1 devices reported in the literature are bipolar switching. Any questions? And then lastly is this ferroelectric memory. This is one of the newest technology. Not really newest technology, but this actually become popular in the recent years. So essentially this depends on some capacitive change, and the ferroelectric material has a polarization switching. So here, if you look at the ferroelectric material, it's a crystalline material. You have this crystal structure. And in the crystal structure, depending on the atom's location, you may have built-in dipole within the crystal structure. For example, here you look at this crystal structure, and those atoms are like ionized, right? So those atoms will be those will be like bound between the atoms. So the atoms like carry the charges. And then here, depending on the location of this atom, it can give you like a dipole. The built-in dipole. Dipole means a pair of positive charge and negative charge. This means dipole. So you can have built-in dipole within the crystal structure depending on the location of this atom, either here or here. So by this atomic displacement of the atom, in this case, you can have two states with a built-in dipole pointing up or pointing down. And this will give you an energy landscape like this. This is like the free energy, Gibbs free energy of the material, depending on the atom's displacement. And you have those two states. So how do we use those two states? You have different configurations in the device. One is called the FE-FET. This is ferroelectric field effect transistor. So here, the idea is to embed this ferroelectric material into the gate stack of your transistor. And here, between the normal metal oxide MOS structure, you have like a ferro layer here in the middle. So the ferro layer will have this built-in dipole. And you can change the dipole configuration by applying gate voltage. So if the dipole is pointing down, then when you read out the drain current, you will have a low threshold voltage. This one, the threshold voltage will be low. And if you have the dipole pointing up, then you will have the threshold voltage high. So this IV configuration is very similar to the flash memory. Basically, you can change the threshold voltage of this transistor depending on the dipole or this polarization state of the ferro material in the gate stack. So we are going to discuss the details later, but this is very similar like the flash memory. There are some differences we will discuss later, but the mechanism is very similar. You change the threshold voltage of this transistor depending on the polarization or the dipole states in the gate stack. The other configuration is that you integrate the ferro material in the drain contact. So it's like 1T1C. This is like DRAM. This is like your capacitor of the DRAM. You change the regular capacitor with the ferro capacitor. Then the ferro capacitor will have those dipole states pointing down and pointing up. So when you sense the 1T1C's current, then if the device is pointing down, then the current you measure from the plate will be low. And if the dipole is pointing up, then the current you measure from the plate electrode will be high when you read out this 1T1C structure. This C is a ferro cap. And we'll discuss the details later. So basically, here the FE-FET is like floating gate flash, and the FE-RAM, this is called ferroelectric random access memory. It's like DRAM. FE-RAM is like DRAM, and you rely on the different readout current from the plate. So this is 1T1C, but the difference is that the C is a ferro cap instead of a regular cap. So your question is this cap, the current will flow through the cap? Yes, the current will flow through the cap in the transient mode, right? So you think capacitor is insulated. That is only true in the DC mode. Right? In the transient mode, when you apply pulse, current flows through the cap, right? You will charge up the cap, right? You have the displacement current in the capacitor, but in this ferro cap, it has additional like a polarization switching current. So you need to apply certain current to flip the dipole state from up to down or down to up. So you do have current flow through this capacitor. It's AC current, right? It's not DC. DC, of course, cap is like an open circuit, but in the AC mode, cap is conducting, right? Okay, so those are the overview of the emerging technologies. And then here, this is a table to compare the metrics for different technologies. And we need to understand this table. Here, those numbers are representative, not necessarily the best number or the worst number in the literature. Those are the typical numbers. And here we have SRAM, DRAM, flash. Flash, we have low flash and NAND flash. And the emerging non-volatile memory, we have phase-change memory, RRAM, STT, MRAM. And we have one more candidate we haven't discussed yet. This is a special class of the MRAM, the SOT MRAM, spin orbital torque MRAM. We will discuss that later. And we have FE-RAM and FE-FET. So first, the cell area in terms of F square. And we discussed before, like SRAM larger than 150 F square, and depending on your W orbital, can be like 300 F square or even more than that. DRAM typically is 6 F square, and no flash 10 F square, and NAND flash is a two-dimensional space, like 2 F square, and then you divide it by the MLC. And then if 3D, you need to divide by the number of layers. So that's why NAND flash is the lowest cost per bit. And then generally the other emerging non-volatile memory may have those like a wide range of the cell area, as low as 4F square. If you do the cross-point array, we will discuss that in later. And if you do 1T1R array, then you may have like 50F square or even 100F square, depending on the transistor's width. So here you see that this is better than SRAM, but not as good as DRAM or the NAND flash. And multi-bit, like SRAM is 1 bit, DRAM is 1 bit, like NAND flash, you can have TLC, QLC, like 3 to 4 bits. And the emerging non-volatile memories, typically you can do 2 or 3 bits, like phase-change memory RRAM, FRAM, FE-FET. FRAM is 1 bit. FE-FET can do 2 or 3 bits, and MRAM is always 1 bit. We will discuss the reason later. And the voltage, so typically the non-volatile memory, emerging non-volatile memory, is like 2 to 3 volts. It's better than the flash, not as good as SRAM. So it's higher than the logic VDD, but it's not as high as flash, using like 10 volt, 20 volts. And MRAM is good. It can be compatible with the logic. MRAM typically like 0.5 volts, you can switch. So the read time typically of those emerging non-volatile memories, like tenths of nanosecond, is very typical. And the fastest is this SOT MRAM, can be almost like 1 nanosecond. So only this one has the potential to reach the SRAM speed. Others are like DRAM-like speed or low flash-like speed. Of course, much faster than the NAND. NAND is slow. We discussed why. And the write time typically is like tens of nanoseconds, up to like 100 nanoseconds. And SOT is also faster. So in general, if you want to have the high speed, then SOT may be a good candidate. And then retention. This is non-volatile memory, so that's why you should have some retention, like 10 years or at least a few years. So this is like a non-volatile memory, similar as flash. And then endurance, how many cycles you can write the data. So here NAND flash, today only like 10 to the power 3 or 10 to the power 4. And then SRAM and DRAM should be very good endurance, like theoretically it should be infinity. And if you look at the numbers, should be larger than 10 to the power 16. This is estimated for 10-year lifetime. Yeah, and every like a few nanoseconds you write once, then you will get like 10 to the power 16. And the non-volatile memory generally is somewhere between the flash and the SRAM and the DRAM, typically like 10 to the power 6 or 10 to the power 9. And the STT-MRAM is the best among the non-volatile memory, like STT or SOT-MRAM is getting close to 10 to the power 12, 10 to the power 14 in that range. And then the write energy, joule per bit. So SRAM is very small. You rely on the charging and discharging of the parasitic cap of your storage node, like femtojoule. And DRAM, you rely on the external cap at a vertical, like a 3D cylinder stack capacitor. Then you need like tens of femtojoule to charge up that cap. And no flash hot electron, so you pass large current. This is very bad in terms of the current because the write efficiency is low in the NOR flash. And NAND flash, although the time is long, but the current is really low, relying on that FN thoroughly. So the current at the cell level is pretty low, like tens femtojoule. Of course, NAND flash has a problem that you have to, if you consider the parasitic cap, you have to charge the long wires of the VLAN or the bit LAN, then the energy is high actually at the array level. But at the cell level, if you only consider the floating gate transistor, then the write energy is low. And then the emergent non-volatile memory typically is in between, like the SRAM and the NOR flash. The phase changing memory is the worst in terms of the energy because this one relies on the temperature, and you need to heat up the material by injecting large currents. So the write energy is not good. And the other memories, like generally like a picojoule, and the best in the emerging non-volatile memory is the FE-FET. So this is getting close to the SRAM level. The reason is that in the FE-FET, you do not pass the DC current. You flip the domains. You apply voltage to the gate of the transistor, and the gate does not really pass the current, does not pass the DC current, only the AC current. Therefore, the resistance, the energy is low in this case. So I already presented the comparison between those memories. And then the question for you, right? If you look at this kind of table, and then the question for you is that, how do you want to apply those emergent non-volatile memories? What would be the application space given those metrics? So then how would you assess the emergent non-volatile memory? Can they replace SRAM? Yes or no? Or anyone like getting close to SRAM, right? So here the green numbers means good attributes, right? This is what you want. And then the red ones are really bad attributes. Of course, SRAM is large in the cell area, but speed is really fast and very hard to compete with SRAM in terms of speed. If you need the speed, then none of those emergent non-volatile memory can compete with SRAM. Maybe the SOT can get close, like maybe L3 cache maybe getting close, but for L1 cache, there's no other candidate that can serve as L1 cache. If you need the speed, like you need to catch like your clock frequency, like 2 gigahertz, 3 gigahertz, that means 0.5 nanosecond or 0.3 nanosecond. There's no other memories that can have this speed. And then the NAND flash, like no other memories can replace NAND flash. Why? Because the density. NAND flash will have the 3D, and then you know how small the cell, the equivalent bit area is. So it's very hard to compete with NAND flash in terms of the cost. So then all of them at least can replace the low flash if you compare those metrics. And DRAM is also hard to compete with. One is because of cell area. The other reason is the endurance. For DRAM, you do need to write very often, very frequently, and it's very hard to have the same net density and endurance for the DRAM. So the conclusion is that there's no memory that can replace DRAM, replace NAND flash, replace SRAM. So there's no other memories that can replace those mainstream technology. What you can do with those emerging non-volatile memories to supplement the gaps in the memory hierarchy, or find new applications instead of replacing the existing mainstream technology. And we will discuss the applications later for those emerging non-volatile memories. And one of that is embedded non-volatile memory to replace no flash, for example. And also those non-volatile memory can enable the in-memory computing. We will discuss that later. All right, so let's look at the possible applications. So as we discussed, it's very hard to compete with L1 or L2 cache, but STT-MRAM or SOT-MRAM may have a chance as L3 or even L4. You can create another level L4 cache. They may have a chance because the speed requirement is reduced as you move farther away from the processor. But the STT-MRAM or SOT-MRAM may give you larger capacity than SRAM in this level. Right? So in this level, at the bottom of the cache, what you need is larger capacity, and the speed requirement can be relaxed, can be reduced. So they may have a chance here. And the RRAM phase change memory, FE-FET, they are good for the read-intensive embedded memory applications. Here, they are good in the read, and actually FE-FET is maybe also good in write. But at least RRAM phase change, the read properties are good. The write, still they need to have like large current, large energy. So here, there are new applications that require this read-intensive embedded memories. For example, the machine learning inference engine. So we are going to discuss this in the very end of the semester, the last lecture. Actually, this is also my research area. So if you use those memories for the inference engine, inference means you only read, right? So after the neural network is trained, then you only do the read operation of those weights. So if you only do read, then no write. Then what you need is a large capacity embedded memory to store those weights on chip. And those emerging memories may be a good fit for the inference engine design for the machine learning accelerator. So those are new applications beyond the traditional memory hierarchy. And there's a new level between the main memory and the SSD, so-called the storage class memory. And the 3D version of the RRAM and all the phase change memory may be a good fit with this. So you need a higher density than the main memory, the DRAM, and you need faster speed than the SSD. So this is called a storage class memory. And the 3D X-Point is a commercialized product from Intel, and you can buy it from the market. They call it Optane SSD. It's a high-end SSD made of the 3D X-Point, the 3D version of the phase change memory. And then this is a good fit to this storage class memory. It's a high-end SSD. You can think it's a high-end SSD, faster SSD than your regular NAND flash-based SSD. And then in the future, if we can do the 3D FE-FET, because as I discussed, the FE-FET has a very similar principle with the floating gate transistor or the charge trap transistor, where you rely on the a threshold voltage change. So in principle, the FE-FET is compatible with the 3D NAND flash process. And if we can do the 3D version of the FE-FET, then it may have a chance to change the NAND flash or the SSD if you can have the 3D vertical NAND flash made of the FE-FET instead of the charge trap transistor. Then it can be much faster than the NAND flash based on the charge trap. So they may have some chances there. So here is like an outlook for the future of the memory system. If you have those non-volatile memory emerging technologies to be mature, then you may have those applications enabled by those new technologies. But they are not there yet. Okay, this is just an like an outlook for the future. Industry is still doing R&D of those emerging technologies. Some of them are getting close. Some of them are still in the early stage of the research. And we will discuss those one by one in the following lectures. So any questions here? Okay, in terms of the research, here this is a summary from the prototype chips reported in the major conferences like ISCC, VLSI, ADM. In terms of the capacity of a single chip reported, and here this green one is a flash, NAND flash, and we have 3D NAND flash, and you see the 1 terabit as we discussed before, like by all the major companies. And then the emerging non-volatile memory, like the biggest is the 32 gigabit RRAM reported like a few years ago by SanDisk. And then the phase change memory like 8 gigabit reported by Samsung a few years ago. And the MRAM like STD MRAM like 4 gigabit reported probably by Everspin, a startup company. And the FE-RAM, this is the first generation of the FE-RAM, and the material is PZT based, and it's typically like hundreds of megabits, and this one has commercial product as well. So you see from the density point of view, they are lagging behind of the NAND flash. There's no way to catch up the NAND flash because NAND flash, as we discussed, they're moving towards 256 layers, and it's impossible for those emerging technologies to build like 256 layers. There's no way to compete with NAND flash in terms of capacity. And also here you see that the SRAM actually is also improving over the years because of scaling. So I believe this is a 5 nanometer SRAM from the TSMC a demonstration. 5 nanometer is the latest technology available today. And you can have 128 megabits cache on chip. so it's not bad actually. SRAM in terms of capacity. And the DRAM, like HBM, if you do the HBM, we discussed you have multiple dies, and if you stack that by the TSV, you can get 128 gigabit per stack. So the DRAM is also good in terms of the capacity if you do the 3D stacking. So you see the emerging memories that are in this space, and it's hard to compete with DRAM and NAND flash, but they may have some chances to beat with SRAM in terms of the capacity on chip. So here the goal for them is to make them embedded on the same chip with logic. Because for standalone memory space, it's impossible to beat the NAND flash or the DRAM standalone memory. Therefore, those memories should be embedded to the logic. Then you may have some chances to beat the SRAM. And then from the density point of view, so this is just the capacity, the total number of bits on the chip. But if you normalize the number of bits, let's say megabit per millimeter square, you normalize the bits to the area of the chip. The NAND flash, as we discussed before, getting close to like 10 gigabits per millimeter square because of the 3D, because of the PLC, QLC, right? And then the other technologies, for example, the Intel's 3D exponents give you like 600 megabit per millimeter square. This is better than the 18 nanometer, the contemporary like DRAM product. So this 3D exponent, 3D version of the phase change memory, indeed makes the density between the flash and the DRAM. So that's why this is a storage class memory, right? Storage class memory. And MRAM, this 4 gigabit MRAM, give you like 38 megabit per millimeter square. This is barely better than the state-of-the-art 5 nanometer SRAM. 5 nanometer SRAM give you 30 megabit per millimeter square in terms of the density. So here is the comparison in terms of the density. And then the bandwidth for the write and the read. Write and read. And here you see this data point from the prototype chips reported in the ISCCs. And here I believe the red ones are the flash, and flash is slow, right? Flash, the bandwidth is low. And flash, actually you may have the NAND flash and NOR flash, and NOR flash is typically here. NOR flash good in read, right? NOR flash is faster in read, but NOR flash write is also slow. And then those are probably the NAND flash. And the emerging non-volatile memory, like the STT-MRAM here, you see it's both good in the read and write. So basically, this towards this corner, this direction is good because you have better read and better write simultaneously. So here, some of the emerging non-volatile memories outperform the NAND flash. They should outperform the NAND flash because NAND flash speed is low anyway. But they are not there yet to compete with the DRAM, especially HBM. Because HBM you have wide I/O, and then you can have very good like read and write bandwidth for the latest HBM 3rd generation. So any questions? Okay, next we are going to discuss how we integrate those non-volatile memories into the array. And the first configuration is called 1T1R array, one transistor, one resistor array. As we discussed before, right, so this is a variable resistor for like the R1 phase change or the STT MRAM. So it's a two-terminal device. But when you integrate this into array, you may still need a selected transistor in series with the resistor. So this is 1T1R array. And the transistor gate is controlled by the VLAN, and the transistor source is connected to the source LAN, and the other end of the resistor is connected to the bit LAN. And if you look at like this cartoon figure, it's like something like this, right? So VLAN is the gate of the transistor, and those memories are integrated to the drain contact. So you have this resistor here to the drain of the contact. Because it's two-terminal device, you can vertically stack like 3 layers at the drain contact. And if the W over L of the transistor, still you know this is your W, this is like your L. W over L is 1, then the typical cell area can be like 12F squared. And the minimum cell area can be 6F squared. Why is that? This 6F squared reminds you what? The DRAM, right? If you use the DRAM layout, you probably can get 6F squared because you have that transistor. Essentially, if you look at this one, it's very like DRAM array, right? If you think this, if you replace the capacitor, a resistor with a capacitor, then it's like a DRAM array, essentially. So if you use a DRAM layout, then you may theoretically achieve 6F squared. But in reality, it's very difficult to use the DRAM layout. And one of the reasons is the transistor's width could not be minimal. And we'll discuss that in a minute. But before that, let's look at the write and read scheme for this 1T1R array. For the bipolar switching, this bipolar switching. So for the set process, what you do is to select this cell by turn on the VLAN here. So the VLAN is turned on. And then you apply the set voltage pulse from the bit LAN to this cell. And then you ground the source LAN. So you have more positive voltage across this cell. And if your voltage is large enough, then you can set the cell to the low resonance state, on state, or the 1 state. And other cells will be either half selected or unselected. And if you want to reset, then what you can do is to still turn on the VLAN. So VLAN is turned on. And then you change the set or reset pulse to the source LAN. Here you apply to the source LAN. And then ground the bit LAN. So here in the set case, the current will flow this way, right? But in the reset case, because you apply voltage here, current will flow this way. So bipolar switching means you have to change the voltage or the current polarity. And then you can reset this cell to the high resonance state or the off state. And then for the read, you still need to turn on the VLAN to select this cell, and then apply the read voltage to the bit LAN. And then you can sense the difference in the resistance through the current to the bit LAN, and this needs to be attached to the sense amplifier. So the challenges in the 1T1R scaling is the programming current or the write current of the cell. you need to pass enough current to change the state. And the current is limited by the series transistor, W over L. You need to have enough W over L to give enough current to write the resistor. So here is a survey of different technology in terms of the write current. This is the write current with respect to the tech node. And you see that most of phase change memory need high current, even larger than milliamp for the older technology node. The reason is that phase change memory, you need to pass large current to heat up the material. So the current is high. And then the STT-MRAM is the green ones. You still may need like hundreds of micron. And RRAM has a wide range. Many of them actually are still here. It's tens of micron or hundreds of micron. And here the three gray lines are the drive currents for different transistors with different W over L. So even W over L equals to 3, you can only provide like up to like hundreds micron. Therefore, you cannot use the minimal transistor, which is W over equals to 1, to drive the 1T1R. For those cells, you may need like W over L, like for example 6. So that means the cell area is limited by the W over L. If you think about the layout, right, of the transistor. So here you have the contact source line contact, bit line contact at the drain side, and the resistor is integrated here. So the resistor does not need to take much space. What takes space is the W over the L. Because you need to pass large current, you may have a large W, right? You may have a large W. So the cell area is limited by the current that you need to pass to switch to write the cell. And the second array is called the cross-point array, or this X-point array. And this is what Intel used. And also it may be called crossbar array. So the idea is very straightforward. You get rid of that transistor, and you still have the resistor at each cross point, but you need to add this so-called selector, a two-terminal device in series of the resistor to select the cell which you want to program. So essentially, this is like a crossbar array. You have the word lines, horizontal, and bit lines, vertical, and each cross point you have one cell. But this cell is made of one selector, one resistor. It's called 1S1R cell. And from the cartoon figure, you can see that you have this word line and bit line, horizontal and perpendicular to each other, and each cross point you have this vertical stack, and the stack is made of 1S1R. This R can be either R1 or phase change, and STT-MRAM is difficult to be integrated because STT-MRAM's on-off ratio is very small, and the sense margin will be very small if you do this 1S1R array. But the R1 and phase change, you may have opportunities to do this 1S1R. And this is what Intel and Micron commercialized with the phase change memory in this 1S1R array. So here, theoretically, you can get 4F squared in the two-dimensional space, right? So here you only have the word lines, bit lines, as we discussed. If you have one wire like this, then you get 4F squared for the cell, because you have 2F for the wire and the spacing, and 2F for the wire and spacing between wires. So theoretically, you get 4F squared in the 2D space. And if you stack this into vertical like direction, you will get the 3D exponent, that is 4f squared divided by the L, and L is the number of the layers you do the 3D stacking. This is exactly how Intel is doing these days. Okay, let me look at the time here. I'll still have a few minutes, so let's try to finish this one. So how do you write the data into this cross-point array? So here is the principle. We have the V over 2 write scheme for the bipolar operation. So what you want to do is to apply the write voltage, like VDD or VWrite, to the selected line or selected row. And then for the selected column for this cell, you ground. Okay. So that's why you have the VW across this cell to write the cell. And for other cells, you don't want to write, so you need to half select or unselect them. So what you do is to for those unselected lines, you apply half VDD, half V. And all the unselected bit lines, you do half V. So the black ones are half V. And if you check the voltage across other cells, for example, this cell along the same line, you will see that this is V, and then the other end is half V. So the voltage across that will be half V. And similarly, this one is half V, half V. So the principle is that, or the assumption is that half V will not write the data. Only the full voltage V will write the data. So here those cells are half selected. And similarly, you can check along this green bit line, you will have half V across those cells. And for other cells of the bit line or of the selected bit line or selected word line, for those cells, because those ends will be half V, so the voltage across that will be 0. You can verify that by yourself. So only this cell will see the full voltage drop, and only this cell will be right. And if you want to reverse this by the reset, what you can do is simply flip the selected row or selected bit line or word line to be 0, this green line, and then the selected column or selected bit line to be your write voltage V. And this cell will see a negative V. For the bipolar situation, this is what you want. And you can verify that other cells along the column will see half V. Along the same word line or same bit line will see half V. And others will see 0. So this is a principle for the half write voltage scheme. And you will have some homework related to this kind of question. And you can have, if you want to write multiple cells, you can do that in this sequence. For example, if you want to write this word line or this page, for example, this is the data you want to write in. So first you can write ones. So you can do that in parallel. So those are ones. So you can have V here and ground all the cells that you need to write to the 1. So you write them in parallel. And then you write the 0. So for the rest, you want to write those to 0. Then that means you have to ground here and apply voltage to those cells you want to write 0 from the column side. So you need to divide that into 2 steps to write this sequence into the array. So let me look at the time. Alright, so we run out of time and we will stop here today.